RIS. So I am an assistant professor at VNIT Nagpur, which is one of the NITs like NIT Trichy, and we are located at Nagpur, which is the orange capital of India. So a lot of oranges. Actually, this season is of oranges, and we have surrounding Nagpur lot of forest reserves specifically for tiger safaris and those things. So like Tadoba, Pench, all those tiger reserves are there in the vicinity of Nagpur. This is the VNIT main building, like admin building we call it. So when you enter from the main gate, it looks like this. This is the night view of this. So like other NITs, we are also one of the NITs and converted. We were first the Regional College of Engineering, and later we were converted into NITs in the year 2000. We are very much in the heart of Nagpur city. Means it's not like outside Nagpur. It is very much in the middle of the Nagpur city, and we have around 215 acres of area and more than 5,500 students on campus. This is the department of EC where I work. Like we offer BTech, MTech, and PhD programs, and we our UG and PG courses are accredited by NBA, and the entire department is actively involved in research and development projects and consultancies in all the areas like communication, signal processing, biomedical, photonics, all such areas, antennas we do cover in our research and consultancies. So today I'll be talking about basically on RIS and full duplex wireless communication systems, specifically the combination of RIS and full duplex communication systems. So I would be giving you the background of each of these two technologies. One is the reconfigurable intelligent surface, other is full duplex system. So I would be giving you the basic idea of these two technologies, and then the motivation why should we combine these two technologies, and then we'll take up one analytical problem and we'll analyze the performance of that problem, and then I'll be discussing the open research problems. So those who are pursuing PhD or looking for a PhD problem, I have explored 5 such research problems, like which can be attempted or kind of open problems in and as per the current trend in the literature. So this is going to be the general flow of my presentation. So like we are almost witnessing the the evolution of 5G in our country. It has, like, people are claiming that it has been deployed. Yes, most of the cities and places we do have 5G technology as far as cellular telephony is concerned, but the true use of this 5G technology is yet to be achieved, and specifically in the use cases and different applications where the promises of 5G technology can truly be exploited. So contrary to the other generations of wireless communication systems, the basic focus of this 5G technology is on flexibility. So this flexibility can be in terms of multinumerology, multiplexing in a single frame, or it can be use of different realization of the same parent waveform, and then it provides us the foundation for flexibility in terms of physical layer of the wireless communication systems, which is going to pave the way for the next generation of wireless communication system, that is 6G or beyond 5G systems. So if we explore the flexibility beyond 5G, the basic starting point becomes the physical layer. So in physical layer, one of the promising technology to have a flexible, flexibility. Is there any query from a
No, sir.
participant?
Participants, please mute yourself. Yes, sir. You can continue.
Okay. Yeah, I request, like, if there is no query, please keep yourself muted so otherwise it disturbs, right? So it's like I was talking about the flexibility in 5G and beyond 5G systems. So uh, what I'm trying to connect is how from 5G we can move to 6G, and RIS can play a role there, because RIS is more about reconfiguring the propagation environment in a way, in a desired way, right? So this is a kind of flexibility which we can exploit for the evolution of next generation of wireless communication systems. So, if you see the first generation to sixth generation systems, like in 5G, the transmitter, nowadays we do have, a lot of flexibility, because earlier the transmitters have kind of standard defined. Now we have only few essential rules for transmitter and receivers, but we have a lot of flexibility. Channel has been, kind of random from one's first generation to the current generation, fifth generation, which we are trying to control. And probably, in the next generations of wireless communication systems, we can look for, or we can envision a wireless communication channel whose properties can be controlled, right? So RIS is one of such potential technology to control the propagation environment. Transmitter, channel, interference, and receivers, in these terms, if you analyze the flexibility, so we are at 5G also we are having a lot of flexibility, and the evolution of next generation standards are basically more about how we can have flexibility and control over that flexibility. So, in terms of applications, if we go and see the next generation or upcoming wireless communication systems in terms of use cases, so we have heard a lot about ultra reliable low latency communication. Then we do have massive machine type communication, and we do have EMBB, right? So ultra reliability, low latency, and location precision. Then there are applications which demand high throughput, enhanced spectral efficiency, and extended coverage. We do have the another vertical where the better energy efficiency, low complexity, and extended coverage. So one of the technology, or one of the key idea which can actually which can work as the intersection of all these three verticals is the full duplex wireless communication. So, and basically the multi-user full duplex wireless communication. So, multi-user systems and user pair scheduling, it is all about the connectivity. So, with the increasing connectivity, a lot of devices are now expected to be connected to the network. So, we do have exponential increase in the number of devices which are going to be connected to the network. Then those devices are to be served by given resources. So the uh, resources are to be shared among the devices, so excess of the resources is to be scheduled, right? So that is one of the ideas where the next generation systems are going to look into. Then we do have another possibility where we can work on the spectral efficiency aspect. We can compare the traditional duplex techniques versus full duplex. So if you all remember, or maybe you do have a fair idea about FDD or TDD. So we do have frequency division duplexing and time division duplexing. For example, nowadays, like if you remember, initial definitions of simplex, half duplex, and full duplex systems was, simplex is something where we can only transmit one way, and then half duplex came where we can transmit both ways, but one at a time, or one in a in a frequency manner we can divide the resource. And then the full duplex means you can simultaneously downlink, uplink, but either in time or either in frequency you are doing. So this full duplex interact full duplex exchange of information, it was it is being achieved by either frequency division duplexing or time division duplexing, right? But this full duplex communication system is sort of a different idea, where the transmission and reception of the data, it happens two frequencies separately for uplink or downlink, or two time instants, for one for transmission and one for reception. We are not doing that. We are transmitting at the same time, receiving at the same time in the same frequency, right? So this is the idea of full duplex wireless communication system. So we do have, arising from full duplex wireless communication system, we have a better spectral efficiency, and we can have different applications where two-way or one-way full duplex relaying can be thought of. Like, so the different applications of this full duplex, this thing is, one is like, you can classify the systems in terms of full duplex two-way relaying or one-way relaying, or you can have, reliability or latency. When you are going for ultra reliable low latency communication, you can have finite or infinite block lengths. So like key applications, we know IoT network, where a lot of multiple devices are there which are, accessing the internet. Then there are mission critical communication. Then for improving coverage, because there are a lot of users you may find at the cell edges, you have to provide the coverage to them. Then cooperative cellular, unmanned aerial vehicle enabled systems, all these systems are, part of the next generation wireless communication system, where full duplex things can be helpful. So as I mentioned, scheduling schemes, are mandatory or sort of requirement, because uh, multiple users are there to access the finite number of resources. So there would always be kind of arbitration, always kind of, access problem between uh, among the users. Then mobility of nodes, it is going to play a role. Like when the users are mobile, the Doppler come into picture, and then they have, different time selective fading. Uh, in full duplex node, if you are considering the full duplex node, self interference is kind of a main villain in the story, because it suppresses the desired signal which is coming from the different or far location. So just to describe this, suppose there is a user talking to another guy, right? And there is a full duplex node which is acting as a relay. So this is sending the data hello, right? And then this is receiving the hello data and sending it in the next instant to this guy. So when this will be sending hello, so the message was hello Jack. So when this is sending the hello Jack, because this node is simultaneously transmitting and receiving in the same frequency in the same time, so whatever is being transmitted, means this hello which is being transmitted from this antenna, will also be listened to by this antenna, right? So this hello will come again to the receiving antenna of this same node, right? Because this is a full duplex node. And so when this receiving antenna of this node is receiving the message from a distant user which is saying Jack, right? This is also receiving the message from the same user, and this is going to be a interfering and self interference, right? Interference happening because of the node itself. Now you may ask the question, like, if this guy already knows that hello is what was being transmitted, you just subtract the hello from the message you are receiving, right? But this is not a kind of arithmetic addition or subtraction. This is sort of the interference of two signals, one at a which is coming from a far distance. So it is actually having a very poor signal strength or lower signal strength. And this guy, because it is coming from the same antenna, same from a different antenna of the same user, this is going to have a higher signal power, right? So this interfering signal is kind of a strong signal which is going to play, which is going to suppress this incoming desired signal. So this signal which is coming, from, which is arising because of the, yes, please, if there is doubt.
No, sir.
Okay.
Continue, sir. Please continue.
Yeah. So if, because the signal is coming from the from the same antenna of the node itself, it is, the distance between these two antennas is very less. So this is going to be a high power signal compared to the signal which is coming from a far distance, right? So this signal is called the residual self interference or self interference, or sometimes it is also called echo interference, right? Because it is a kind of an echo. Okay, so the modeling or characterization of this residual self interference is very critical, because this RSI signal, it can be 50 to 100 dB higher than the desired signal, right? Right. And because owing to the fact that there are a lot of advancements in the interference cancellation techniques, interference management techniques, you can somehow cancel a lot of this interference, manage this, uh, but it's still, because this 50 to 100 dB power differential is a lot, the algorithms, they may not defeat this high power differential, right? It's still some RSI is going to still remain in the system, which is going to impact your desired signal, right? And basically this is because interference part, it is going to be in the denominator of the signal to noise ratio, which will become SINR, signal to interference plus noise ratio. So it would actually, higher the value of this interference, lower would be the SNR, right, or SINR. So this characterization of RSI is very crucial because of the high power differential, which shows the possible presence of line of sight component between the transmit and receive antennas of FD node. This I already have discussed, right? Uh, Even if you provide a kind of separation between electrical separation, or in terms of that electromagnetic separation between uh, transmit and receive antennas of the full duplex node, still there can be reflections, multipath reflections coming from different directions to the full duplex node, right? So that interference signal cannot be ignored. So in literature, the RSI has been modeled in two ways. One is it has been modeled as a constant power, where like noise we considered as zero mean and some variance, so we assume that the noise has some given average power. So same way RSI has also been modeled. And the other approach where RSI has been modeled as the random feeding distribution, okay, where we model RSI with as a random variable. Okay, so okay, so now apart from, so I told you about the full duplex wireless communication. So it is, just to quickly summarize, it is not about FDD or TDD. It is about in the same time, same frequency, transmission and reception both. So when you are transmitting, you are going to receive what you are transmitting, and what you are transmitting is more is having more power when it is interfering with what you are receiving, right? So this is the main picture of any full duplex node or full duplex wireless communication system. So although, what is the gain of having a full duplex wireless communication system? You can transmit at the same frequency at the same time, right? In the same frequency at the same time, you can transmit and receive. So it is going to make one of the frequency resource and one of the time resource free for you. You need not have you can utilize that additional resource for some other user. Like for example, in uplink and downlink nowadays we are using different frequencies. So if you are having a full duplex structure, then we can just work on with one frequency, like maybe uplink or downlink. Other frequency you can serve any other user with that. Okay, that is the advantage. But the challenge is this RSI or echo interference. It is the major challenge, right? Then this challenge is coming up with kind of with already existing, very critical and randomly fluctuating wireless propagation environment, where channels are, when like if you move to urban scenarios, lot of vehicle mobility and lot of dynamically changing propagation environment is there. So the this electromagnetic propagation or transmission of information from one place to other place, it is in itself, it is a complex and very critical task, right? And then this full duplex, if you consider, there is one more added kind of challenge, which is the eco interference. So to sort of uh, manage or sort of counter these two challenges, one of the idea which is there, which has emerged as one of the potential technology for next generation wireless communication system, is the intelligent surfaces. So I will not be covering this part in much detail. Like, but if you have any question, you can ask about RISs. I believe that many sessions you might have already had on RIS technology. So RIS is basically made up of metamaterials, and you can actually control the electromagnetic property of each of these metamaterial element, and you can control the way they are going to reflect, right? So if you can control the pattern through which or in which they are going to reflect, you can make you can utilize this entire set of elements or entire surface. You can make to either to focus and improve the signal strength at a particular user, or you can also make this to nullify the signal at some other user. But I mean to by nullify, I mean that you can use the RIS for destructive interference also. For example, if there is some war kind of situation, and the location of some enemy receiver, you can focus your signal to kill their desired signal just by destructively interfering into it. So we can have constructive interference and we can have destructive interference. So RIS can be used for energy focusing, so that they can increase the signal to noise ratio at a particular location, at the receiver location. And you can also use it for energy nulling, where you want to have kind of secrecy, or you want to spoil the game of your enemy in warfare like situation. So RIS can be used. It is kind of a promising thing, and good to explore about. So unlike multiple input multiple output technology or cooperative relaying kind of technologies, RISs are quasi passive, means they require a very less amount of energy for their control circuit. They are low power consuming, right? They have very low thermal noise, and they are software programmable. You can program them on the go, and they are very easy to deploy. And you have RISs in different bands, like you have RISs in you can have RISs in microwave band, millimeter wave band, terahertz, or even nowadays people are working on visible light RISs, which can kind of consider as a lens, right, where the lens is used to focus the visible light on a particular point. Then in recent last 5-6 years, or say 8 years, this RIS has evolved, or maybe one of the most explored topic in the literature of wireless communication system. So we do have RISs of two types: active and passive RISs. So active RISs, they have the ability to amplify the reflected signal, or they can even modulate the incoming signal and transmit it to a particular location. And passive RISs are just there to change the phase of the incoming signal and reflect it, right? They do not process the signal as such. Then you can have single function RISs, like where the RIS function is only just to reflect. Then you can also have dual function RISs, which we are Like one of the example of dual function RIS is star, simultaneous transmission and reflection, where RISs can be used for transmission also and reflection also. We'll be showing through one diagram. And then RISs are, their applications involve a lot of 6G applications in wireless system. You can use RISs for communication purposes as well as for sensing purposes. You can use RISs for localization and positioning also. So the just to understand the basic, math of this RIS, suppose this is the RIS and there is a control through which you are controlling the RIS, and with a particular pattern of these elements, right? On, off, or maybe you can have multiple levels of that. You can focus the beam to a receiver where transmitter receiver, suppose they do not have the direct path is blocked. So each of this element is suppose going to provide you the reflectivity constant, or this factor is eta n, like is it for nth element, and the phase is going to be changed by theta n. So if you see the H and G, overall channel is going to be eta n, gn, then this phase coming into the picture. So this is the RIS response element of, it is the response of nth element of RIS, and then Hn, right? So now there are multiple such elements, and if you assume so the overall channel would be the summation of individual such components. So when you will add them up, your received signal is going to be this, right? Now if you assume that through this controller you can achieve a coherent beam forming, so you can utilize this inequality, and it says that this thing is always going to be equal to this thing if your phase is neutralized, right? So if RIS can provide you the mechanism through which you can neutralize the phase of combined channel H and G, right, you can get the maximum value of this identity, and which is maximum value of this expression, which is actually this, right? So so this is I hope this is clear. This is achieved at a particular phase configuration where you are cancelling the phases of channel G and channel H. Now we can also have this was a simple, kind of reflect one single function RIS. Now you can have dual function RISs where the base station, when transmitting to, or whatever the signal is coming from base station, the RIS can transmit some signal to the users which are positioned or located at the back side of this RIS, or it can also reflect these signals to the users which are at the front side of this RIS if you are looking from this side, from the screen side, right? So RIS can do both the functions. It can, some signals can be transmitted through and some signals can be reflected back. So these properties of transmission and reflection also can be controlled. So this kind of RIS is called the dual function RIS. And this is particularly simultaneous reflecting and simultaneous transmission and reflecting RIS. Now how this RIS works, it works in three modes. You may use actually these functions in three manners. One is the mode switching, where you can use the RIS. First it is entirely it is transmitting through, and second it is entirely reflecting back. So this is, you are changing the mode of RIS. The other possibility is you just switch the energy, means the each element, some of the energy is being transmitted through and some of the energy, partial remaining part of the energy, is being reflected back. And then there is time switching. Some elements, they would be working as the transmitter for some time instant, and same element will work as reflector at other time instant. So in star RIS also there can be these three configuration which can be utilized for achieving dual functions. RIS has not just been explored by the researcher in, theoretically, by the researcher in literature, but it's now been, in the talks of different standardization bodies like ITU, 3GPP, and ETSI, TSDSI, which is Indian standardization body. So all these now bodies, they are, have started considering RIS as one of the potential technology for the future generation wireless communication system. However, the specific standards are yet to be evolved for this particular technology. Just to before going ahead with the numerical analytical problem, I would like to give you the idea what we have done at VNIT Nagpur. So in 2020, we received one grant from Ministry of Electronics for developing the RIS. So probably in 2022, we have developed a initial prototype of RIS, right, in the late 2022. Yes. So this, you can see that this is the in-house developed RIS, and like entire this fabrication and those things were done at Nagpur itself. And then we control the current in each of these elements through this backside. If you can see the controller circuit, and then we excited the RIS. We tested this RIS in different environments like indoor and outdoor environments, and we did even testing in anechoic chamber. So all those things we have done. So we could in a given setup at a distance of around 8 meter, 10 meters, we could achieve the SINR gain of not here, maybe just, yes, we could achieve SINR gain of 27 dBs, right, when RIS is on and an RIS is off. So when RIS was off, compared to that, we could achieve SINR gain of 27 dBs when RIS was turned on. And then the with RIS in on condition, we could achieve for a real-time video transmission, we could achieve a throughput of 37.6 Mbps using 64 QAM modulation. So this we have done. So it is probably one of the, I am not sure about it, but probably one of the initial systems of RIS implementation in our country. We done it, and we have demonstrated it in India Mobile Congress 2023 at Delhi when this happened. So like whatever we say in theory, that this RIS is going to increase the signal to noise ratio and is going to improve the system performance. So we could implement that system, and theoretical claims we could verify. Yes, there was the gain in the signal strength. The elements actually were reflecting, and on a given pattern, they were beamforming at a particular location. All these claims were kind of validated, but we could not achieve the theoretically promised the SNR gains, maybe because the losses. Is there any issue, like any question?
No, sir, no. You can continue, sir.
Okay. Maybe because of the material losses, or the process which we have followed. This is kind of simple academic lab kind of processes we have followed during the fabrication of this RIS. But yes, there were significant gains we could demonstrate using this technology. Like with this, I would like to show you. Like when RIS was turned off, the constellation was not proper, but when we turned on the RIS, the constellation was low. So all these things were, we could prove them in our lab. Even we kind of verified the functionality of RIS in open outdoor environment also. So one of the critical issue in the RIS is the spatial correlation. So let me just explain what is this spatial correlation. So suppose if you can see, I'm just zooming it out. This is one of the element, right? This is the other element, and the spacing between them is this. Now because these elements are of sub wavelength size, they are lambda by 2 or lambda by 5. So whenever there is a signal coming to going to strike any of these element, the signal's wavelength is lambda. So the signal is going to going to fall upon more than one elements, right? So there would be kind of correlation between the reflected part which is going out of these two or adjacent elements, right? So that correlation is called the spatial correlation, and that spatial correlation can be modeled as uh, this function, like there's a sync function. So like between mth and nth element, you can find the correlation coefficient between these two element, right? So you can find the correlation coefficient. There is a lot of these expressions are available in the literature. So basically this correlation depends on the wavelength of the carrier and of course the uh, spacing and size of the elements, right? So this is one of the critical challenge in RIS assisted systems, where because the element size is very small and compared to the wavelength of the incoming signal, and it is going to play the role in the performance of the final performance at the receiver of this RIS assisted communication system. So far I have given you the fair idea of what the full duplex technology is, what is the RIS technology, and I also told you that this RIS thing is basically it is implemented, and
సార్ ఏమన్నారు సార్ అదే
yes. So is there any question or query so far? Like I would like to have any query if you have.
No, sir. You can continue, sir. There is no query. We will take the questions at the end, sir.
Okay, sure. So now there is why should we combine RIS and FT? There should be, what are the motivations for combining excuse me, what are the motivations for combining reconfigurable intelligent surface and full duplex wireless technology? So one of the motivation is enhanced spectral efficiency, which is which can be achieved by through RIS also and through full duplex technology also, because full duplex technology enables simultaneous transmission and reception, uplink and downlink, and moreover RIS also facilitates the optimized signal propagation. So combinedly these both techniques, if you put in a combined together in a system, the system's spectral efficiency is expected to be better than to be more, right, improved, and then signal quality also is going to be improved. RIS can not only increase the signal strength, but if you can use the RIS by through in a proper manner, you can actually mitigate the self interference also using the RIS. There are claims in the published literature that RIS can also help reducing the impact of uh, eco interference or self interference on the system performance. Then RIS also helps you to ensure reliable communication in complex environments by significantly increasing the signal strength. Then we can also have the coverage extension, right? We can use full duplex base stations. We can use full duplex base stations for broader reach, and Then star RIS configurations can also be used for extending the coverage to cell edge users. Energy efficiency can also be improved by using RIS and FD. Together, RIS consumes very less power. Specifically, the power is consumed by the controller circuitry, and full duplex system, they also help us reduce the energy usage of the system. We'll tell you like the reason for this is, like, when you are transmitting with higher power, more signal is coming back to your receive antenna. So when we are using the full duplex node, then we always try to make sure that we do not cross the limit of maximum power with which we can transmit. Now for analytical this understanding, I'm just going to explain one system model. So suppose there are two users, user A and user B. They want to talk to each other, right? So we are considering that they are utilizing, each user is utilizing one RIS. So this RIS A is focusing the signal of user B at user A, and this RIS B is there for focusing the signal of user A at user B. Okay, I'm repeating this again. User B is transmitting its signal with the help of RIS A. So RIS A is focusing its signal on user A. Okay, so these users are actually full duplex users. For illustration purpose in this figure, I have considered only one-way transmission and reception. So we have considered only at the user A, right? Now user A is receiving the signal from user B through this RIS. Okay, so it is receiving this signal through RIS. It is also receiving the signal, some signal, maybe it is highly faded, but it is also receiving a direct signal, right? And then it is at the same time, because this is a full duplex node, it is transmitting in the same frequency. At the same time, it is transmitting its own signal to user B, right? So when it is transmitting the signal to user B, this is going to be something like here. Okay, we have not shown that. Now when it is transmitting its own signal to user B, some of the signal, the user B get the beamforming by RIS B. However, some of the signal, this blue signal, which is actually the signal for B, will also come back after only the part of energy which is going to incident on this RIS is going to come back and interfere at the user A itself. And then there is one more component of the energy which is going to be received at the receiver of this user A, which is the self interference. We have discussed it in detail. So finally, during this transmission process, the user A is going to receive basically how many signals? The signal which is coming from user B through RIS, the signal which is coming from user B through RIS-B, the signal which is coming from user itself through RIS-A, and the self-interference signal. These are the signals which a user is going to receive. I hope this is clear. So with these black dots, they are the interference due to reflection from RIS-A, right? All the channels are denoted. So the channel between say user B and RIS-A are B to RIS-IA. Channel between all other users, you can just see, and the self-interference channel is HAA, right? As I told earlier, The same thing will hold for user B also, because this is simultaneous full duplex kind of transmission. So this user is also receiving and transmitting at the same time, and this is also receiving and transmitting at the same time and in the same frequency. So if you see, I told you what signals are being received at the receiver and at these users. So we can define the SINRs. So SNR at user A can be written as this, like, so this is the overall channel. Desired signal is coming from this path, right? At user A, the desired signal is coming from this path. So it is HIAA and then this path, right? So these two are the desired path, HIAA, Hermitian, and then this is the response of the RIS, theta A, RIS A ka response, and then you have the H by HB IA path, this path, right? So the desired signal is coming from this path. I hope you could follow the movement of this cursor, right? This is the desired path. So we will have HIA response of this RIS and then this path. So this, from this path, the desired signal is coming. So it would be in the numerator of the SINR, and then there would be a denominator part, so which will be having signal coming to itself as the self interference HAA square. So it is with power, transmit power of user A, right? And then there is some noise at the user A, which is sigma square A, and then ZBA and ZAA are considered as the constant powers of the reflections coming from RIS B to A and RIS A to A, right? These are the reflections from this. So if you open, or if you expand the numerator part, we can get this expansion, like I have already told you, like in while explaining the RIS, we have NA number of RIS elements in RIS-A. So for all those NA elements, each of the elements will have will contribute to the channel. So overall channel component and reception would be this, right? And like if you can have a optimal RIS tuning, this would be the maximum value of this, because exponential J theta maximum would be 1 when theta is cancelled out to be 0, right? Like that you can maintain it. I'm not going into the details of further derivations, but using these SNRs, you can derive the statistics of SNR, and then you can derive the performance metrics. Different, matrices, different performance criterias like outage probability, then throughput, good port, capacity, then BLER, all those things. All those things can be derived using these expressions. For simulation parameters, yeah, please go ahead if you have any question.
No, sir, no questions. Participants will take the questions at the last. If you have any queries, you just type it in the chat box. Sir, you can continue, sir. Sir?
Yeah, okay.
Yeah.
So these simulation parameters that we have taken are following. So we have taken the number of elements, like until unless specified otherwise in particular result, we have taken them to be 100, and then transmit power we have taken as 25 dBm. The carrier frequency was 3 gigahertz, and the RIS meta item spacing until unless they are specifically mentioned in a figure, it is lambda by 4, and noise power is 0 dB, and the self interference power is average self interference power is 5 dB. Then different reflections as mentioned here, ZBA and ZAA, they are taken as 10 dB, 7 dB, just numerical values of them. We have considered that the user A and RISA are 60 meter apart, and RISA and user B are also 60 meter apart. So these, and the distance between user A and user B is 100 meter. So this kind of setup we have taken, and we have plotted the, let me just zoom this, sorry. So we have plotted the outage probability versus the transmit power by the user B. So outage probability we are finding out it at user A. Outage probability is the probability of received SNR going below certain threshold, right? So this is the function of threshold. We have plotted this for different number of elements in RIS-A, which is assisting the transmission of B to A, right? So we can see that for the case when we have 81 elements, means it is 9x9 grid, then we have this performance. And when we increase it to say 169, so 13x13 grid, so by simply doubling the RIS element, you can get so much of gain, right? So this is not only kind of coding gain, but diversity gain also is involved. So you are not only getting the lower values of outage probability, but also you are getting the change of slope, right? Which is kind of desired thing in any wireless communication system. So okay. Then other thing that we have plotted, other figure we have plotted is of the ergodic capacity. We derived using the same SINR expression, we derived the capacity of the system. Excuse me. So just give me a minute. Yeah. So we have derived the ergodic capacity using those SINR expressions, and we plotted the results against the transmit power by the user B and for different number of RIS elements. So similar kind of conclusion we can get. We can have for 81 element the capacity was this, and for 400 element if we go, the capacity was improved. And these circles, they are kind of Monte Carlo simulation which validate our result. So the simplest conclusion from these two graphs is this, that if you are having more number of RIS element, the system performance improves, be it in terms of outage probability or in terms of capacity, or maybe I have not shown the other metric curves, but for any kind of metric you have a better performance when you are increasing the number of IRS elements, right? The reason for this is the simple that reason, the fundamental property of RIS, that it increases the signal strength. And theoretically, when you are having n number of RIS element, your SNR is going to be proportional to n square, right? So that is the simple rule. In practice, whatever system we have implemented, we do not achieve the similar patterns, but yes, there are significant gain in the signal strength. Then we have plotted, for the interesting parameter, we tried to actually explore the effect of spatial correlation between two RIS elements. So for the element separation of lambda by 16, lambda by 8, lambda by 4, and lambda by 2, we have plotted the outage probability versus the transmit power of user B. So one thing which we can see is this, that the there is a crossover between these values, outage probability, and these things. Value of outage probability there is a crossover at certain value of PB, right? So if you consider this value of probability, this value of transmit power of B, you can see that initially this outage probability was more, and then at this crossover point it started getting lesser, right? And this is true for each of these curves. So we can see that for lower transmit power, the outage probability behaved in a different way. However, when you increase the transmit power, the outage probability reverses the pattern it was behaving earlier. So at higher power, if you can see, the outage probability is worst when you have lower separation between two RIS element. Means if the RIS elements are very much closer, means their separation is just lambda by 16, the outage probability is poor because of spatial correlation or correlation coefficient, this thing, right? And when you are increasing the spatial correlation, when you are increasing the separation between RIS elements, then the outage probability is improving. Okay, then the outage probability is improving, and you can see then when the separation is lambda by 2, then you are getting the outage probability very closer to the case of uncorrelated channels, right? Uncorrelated channels means when there is no correlation between the outage between the two elements of the RIS. I hope this is clear. This plot, it provides you the performance of the system in terms of good put against the transmit power of user B. So basically the good put is a factor that determines the how many number of bits we are transmitting over a slot, which can successfully be transmitted to the receiver. And we are assuming that there is always a sufficient backlog of the data in the transmission buffer. So this throughput, this kind of parameter is called good put. And when we plotted this good put against the transmit power for different values of spatial correlation related to spacing, right? Lambda C by 2, 4, and so we have considered three combinations of the constant R. So R is the constant which is coming in solving the expression. So we can notice here that for constant value of this parameter RA, the good put saturates at lower PB, right? For a given value, suppose you take RA equal to 2. So you take these three plots, right? So these three plots are this, right? For a given value of this, if you are having if you are analyzing this plot, then you can see that the plot saturates, like saturates means the point where it start becoming constant. This saturates at lower value of PB for higher spacing of meta items. So if you are having lambda by 2, right, then it is saturating, say starting point is this. When you are having lambda by 4, then the starting point of saturation is this. When you are having lambda by 16, then it is saturating at a later stage. So one of the observation from this figure is that when you have constant value of RA, which is 2, the good put saturates at lower value of transmit power PB for higher spacing of meta items, right? Now if you see, if you take constant spacing like lambda by 2, so if you take constant spacing, the good put achieved is higher for higher value of RA. So like if you see this figure and this blue figure, now if you are taking lambda by 2, the good put would be higher for higher value of RA, right? Then the another observation is this, that for RA equal to 1 and RA equal to 2, the trends of output, you can see here that there, I told you about this, that there is a reversal around, like here, if you see at PB equal to 13 dB, this similar kind of effect we have observed in outage probability plot also, that initially for lower transmit power there was a different pattern, and at higher transmitted power the output pattern reverses, right? So at 13 dBm and at say 18 dBm, this reversal can be noticed, and this reversal is basically because of the trade-off between the spatial correlation. Spatial correlation is severe for higher spacing for the RIS. Spatial correlation is severe for lower spacing of the RIS elements, right? So I hope this is clear. So I just explained that this theoretically we can analyze, we can combine the full duplex wireless systems as well as RIS assisted systems. We can combine two technologies to increase the spectral efficiency, and we can analyze. I have demonstrated, or I have explained how we can analyze the performance of the systems. Now I would like move to the sort of last section of my talk, where I would be explaining the open research problems which we can consider. So one is the advanced self-interference cancellation. This is kind of an open problem, right? So you can actually use RIS to dynamically mitigate the interference by optimizing reflection properties. This is one of the possibilities. You can integrate artificial intelligence, machine learning models for real-time predictions and adaptive interference management. And then this kind of work is relevant because it is going to enable the lower interference, self-interference power. So full duplex operation would be more efficient, and this can help in going to be a critical step for next generation wireless technology. So one of the open problem is this, where you can use RIS and AI to control the self-interference. Other is the integrated sensing and communication with RIS and full duplex nodes. So you can leverage RIS for simultaneous optimization of sensing and communication paths. So as we know, RIS not only improves the signal to noise ratio, but it also can improve the illumination power at a particular target. So we can jointly optimize the RIS for sensing and communication paths, and we can explore in the same system full duplex for real-time bidirectional communication and environmental sensing. So this is one of the other possible areas where this technology means RIS can be combined with full duplex wireless communication technology. The other thing is, like, we can have different combination or different types of RISs, and for example we can have a dual function star RIS, and we can go for improving energy efficiency and coverage. Like we can develop hybrid active passive RIS to balance energy and performance. Excuse me. And then we can minimize power usage in dense full duplex networks with RIS assistance. So moreover, we can also optimize energy splitting when we are I told you about different modes of or different configurations of star RIS, like energy switching, mode switching, or time switching. We can optimize among these nodes in a dynamic network. The next thing is we can have multiple RISs, and we can use such kind of system in for physical layer security. So we can have multi RIS system multi-RIS full duplex system. So to coordinate multiple RIS to optimize full duplex communication in large scale networks, it can enhance the cooperative FD system for dense urban scenarios. And then we can use it for increasing the security. We can use RIS to focus or beamform the signals and protect the communication between legitimate users from eavesdropper. And we can also do the joint optimization of RIS and full duplex parameters for secure integrated sensing and communication. The next problem is we can go for 6G use cases, like the potential applications which are going to be there in the next generation systems. Like we can demonstrate or we can use FD and RIS for ultra reliable low latency communication, and for massive IoT systems where there are millions of IoT devices which can be served using maybe full duplex relays or RISs, multiple RISs. All such scenarios do exist. We can have low power RIS and FD links. And then there is always there is not lot of research going on in terahertz band of for exploring terahertz band communication, and it is one of the potential technology for next generation communication systems. So we can use RIS there for improving the signal efficiency, signal strength. And then for UAVs like situations, RIS is already being exploited, whether at least theoretically whether we can get the better performance of UAV assisted systems or not. So these are few open research problems. So conclusion is like we can have through combination of full duplex and reconfigurable intelligence surfaces, we can improve the spectral efficiency of the system, and it brings us the energy savings as well. There is a challenge of self interference also, and when you are having two different technologies coming together, there is a need of joint optimization of the parameters. For example, RIS phase matrix and then number of elements, along with the full duplex node parameters like the eco interference power, and those things should be jointly looked into when you are designing a system, combined system of full duplex and RIS technology. So this technology combined together, RIS and FD, they have a vital role to play in upcoming generation applications, like specifically integrated sensing and communication. And recently, if you will explore, people have started focusing on full duplex RIS assisted ISAC, right? So this is one of the upcoming area where people are at least they have started doing the theoretical research. So, okay, thank you for your attention. We are actively working on implementation part of RIS, planning to start, more of AI ML based things in the upcoming times. So, if you have any query or feedback or any collaboration possibility, you can reach out to me at my email ID. Thanks a lot for your attention, and I kept last 5-10 minutes for question answer. If you have any, I would be happy to.
Thank you, sir. Thank you for the wonderful presentation. Participants, if you have any questions, you just try to type it in the chat box and we will take it for you. Sir, I will repeat the questions from the chat box and you can answer to them, sir.
Okay, let me just see if I can also see the chat box.
It's okay, sir. I will repeat for you, sir.
Okay.
What frequency is fixed for reconfigurable intelligence surface in smart home applications?
Like, is it related to what we have implemented at our place, like what surface we have fabricated, or in general you are asking?
Maybe in general they are asking, sir.
So like, so it is not, particular to that RIS, because whatever frequency your equipment are working at, maybe ISM band or 5G, FR1 mid band. So accordingly, you have to design your RIS and fabricate it in particular frequency band. So Actually, RIS is kind of a technology which can be deployed in any frequency range. Theoretically, yes.
Okay, sir. Moving to the next question. What are the key parameters to optimize when deploying RIS in a full duplex system?
So like when we are deploying RIS in a full duplex system, the key parameters are going to be the transmit power, because whatever power we are transmitting is going to come back at the receiver of the same node, right? And the reflections may also be coming back from RIS also, right? Which RIS is going to beam format the same user. So first parameter is power, then phase matrix, right? And then of course the echo interference channel. When I'm saying RIS phase matrix, it includes both eta n and theta n. So I think these are the parameters.
Okay, sir. Moving to the next question. The RIS placement, how does it impact on the interference and also the final result?
Yes, it makes lot of impact. Where are you placing the RIS? Because as far as whatever work we have done, and also affirming it from the available literature, RISs are generally advised to be placed at either close to the transmitter or close to the receiver, right? But when you are changing the location of RIS, certainly its uh, impact is going to be there on the system performance, because when you are changing the location of RIS, the channels are going to be changed, and estimation of those channels would be required, and then you have to modify your phase response of the RIS for the changed or new channels.
Okay, sir. Moving to the next question. How does the number of RIS elements impact the efficiency of self interference cancellation?
Yes, so if you, there are two ways like where we can look into this problem of so one is like managing the self interference. So self interference can be managed. See, finally the self interference is minimizing your or it is reducing your SINR, right? Because it is a term in denominator. So the overall impact can be compensated by maximizing the numerator, right? For a given self-interference situation, you can maximize the numerator, which RIS can very well do, right? So more the number of elements, better is the signal strength you are going to get, and better is your numerator. So better would be your compensation against the self-interference. One way is this. Other way is, I'm not sure, actually we have not explored it yet, but it is kind of an open issue. We can use RIS to cancel like energy nulling kind of scenario to cancel the self-interference. So which like we have to do the simulations and have to check.
Okay, sir. Moving to the next question. What are the challenges we may face in prototyping star?
Lot of challenging. Star RIS we have not implemented. We have implemented so far the normal RISs with different configurations of it, like polarization sensitive, polarization insensitive. All those things we have fabricated and demonstrated in our lab. A lot of challenges, and they are almost same. Whatever challenges generally we face during any hardware implementation, the similar kind of challenges we faced, specifically in controller designing and putting the and controlling the actually the current in a single RIS element. It was quite challenging task.
Okay, sir. Moving to the next question. Spatial correlation results from the design of RIS itself. Is it correct or not? Then which design is better, with or without spatial correlation?
Of course, without spatial correlation, you will always need, right? And yes, it arises from the design of RIS. True.
Moving to the next question, sir. What role will RIS play in the development of future wireless technologies such as 6G?
Yes. So like these standardization bodies, ITU, 3GPP, TSDSI, all these bodies are considering RIS as a technology for future. So I too believe, see, there are always two voices. Few people always believe that RIS is kind of, a work for theory. But I am a believer of RIS technology that is going to play the role in next generation wireless communication system, significant role.
Okay, sir. Moving to the next question. How thin are the RIS? How to maintain the RIS due to environmental effects?
Can you please repeat the question?
How
Maintain
thin?
RIS?
Maintain the RIS due to environmental effects.
Is it about rains and those things? I'm not sure about the context of the question.
Okay, sir. Then we will move to the next question. How is artificial intelligence and machine learning being used in the context of RIS for optimization and management?
So RIS is being used for, AI and ML, they are being used for the channel estimation. See, RIS element or overall RIS is going to provide a phase, right? Phase control. So that phase matrix, it is going to be it is going to be a difficult task to obtain that particular phase, like what is the phase of incoming channel between the user and RIS, and outgoing channel between RIS and user. So estimating that channel, cascaded channel, and then providing, come up with a perfect phase cancellation is a kind of task which I feel that AI and ML can help in doing that.
Sir, moving to the last question, whether the diversity gain achieved in RIS is equal to MIMO system with 64 cross 64 and N equal to 64 in RIS.
Oh, particularly specifically, I may not be able to answer. But yes, RIS also provides the diversity gains. However, I'm not sure for a particular case of 64 cross 64. We can search the literature for that.
Okay, sir. Thank you. And the questions are completed in the chat box. Swarnima, you may hand over the session to you.
Thank you so much, Sai. Thank you so much, sir, for that insightful and thought-provoking talk. I think the open questions and that open issues that you have given will be helpful to everyone working in that area. Thank you so much for joining and putting in your time and effort, sir. Thank you so much.